All right, you guys ready to get started?
Yeah.
Okay. First, let's start off with our review. Thank you, sir. We'll start off with what is cold.
We didn't sign in yet.
Oh,
Sorry?
What's that? Total absence of heat, absolute zero, minus 460 degrees Fahrenheit, 0 degrees Kelvin, 0 degrees Rankine, negative 273 degrees Celsius, where all molecular motion stops. That is absolute zero. What is heat?
Energy.
Anything above that.
Anything above that, and it's also energy. Yes, that's correct. And the first law of thermodynamics.
Energy cannot be created nor destroyed.
We transform from one form to another. And if you did some of the homework, you should have seen in there that also has the law of conservation of energy as well. Okay. And the second law of thermodynamics.
Heat seeks cold.
Heat seeks what? Cold. Cold, yes. Heat moves from a warmer area or space to a cooler, less heated area or space, or heat seeks cold. And then what affects the speed of the second law of thermodynamics?
Temperature difference, surface area.
Yes, temperature difference and the surface area. What is the definition of refrigeration?
Remove heat from a place that's unwanted into a place that makes no difference.
Are you guys going to be working with refrigeration?
Yes.
Yes. I think it's important that we know that.
Yep.
Yes, it is. Because that's what we do. Everything that we do. All right, before we do that next one, we'll go to this one. All right, BTU. What does the letters BTU stand for?
British thermal unit.
British Thermal Unit. And what does it mean?
Amount of heat required to move 1 pound of water to 1 degree Fahrenheit.
Yes. And sensible heat. What is sensible heat? Yes. And more in the detailed side of it?
Change the temperature without a change of state.
Good. And what is latent heat?
Hidden heat cannot be measured.
Are you just reading it, or are you guys knowing it? If this was a pop quiz, and you just had a piece of paper in front of you with blanks on it, how well would you be doing?
Pretty good, but it's damn near impossible to not look at it when you ask.
No, I get that, but when I only hear 1 or 2 persons going, that is what worries me. Looking at it's not the issue, but if we look at it and we know it, we should just be able to pop it off. So the whole right. That's what worries me. Evaporation and boiling. See the worry. See, this is what worries me.
Substance changes state from liquid to vapor and absorbs heat.
Yes, absorbs heat. It's extremely. Why is that important?
Because that's the whole process, is what it does.
It's everything. What are we trying to absorb heat from?
The liquid, where we don't want it.
Where we don't want it. That's exactly right. We're trying to absorb heat from a place we don't want it. Refrigeration, we want to remove heat from a place that is unwanted. So evaporation and boiling is about making a refrigerant boil, change state from a liquid to a vapor to absorb heat from a place we don't want it. Right? That's what it's about. That is what it's about. Now what is condensing?
When you go from vapor to liquid, vapor to rejecting the heat that you absorbed.
Rejecting heat. And where does that apply? And that applies here. To a place that makes a little no difference, or the more modern one, to a place that we could use it more effectively. Right? We're going to dump the heat out. We're going to absorb the heat into evaporation. And evaporation is what kind of heat? Latent heat. And we use that latent heat to change the sensible heat of the air, to make the temperature of the air drop. Yeah. Or I can do heating. If I turn temperature up in the thermostat and we burn some fuel, what's that going to do to the heat in the air?
Make it warmer.
Make it warmer. So that's going to be adding what kind of heat to the air? Sensible, yes. All right, and then very, very, very important, saturation.
Yes,
PSIG, converted temperature. That is the most important. It needs to be, bam, immediately, PSIG, converted temperature. And then the other words that it means?
Boiling point.
Boiling point, yes.
Condensing
point.
State, latent heat.
Change of state, latent heat, liquid and vapor both exist at the same time. Here I have liquid and vapor in this tank. Are they present at the same time?
Yeah.
So what is it going to be at this tank? Saturation. So if I got the pressure of this tank, and the pressure of this tank shows just a little above 200, looks like it's just barely below, is it 5s? 5, 10, 15, 20. Yep, so 200 and, looks like 204 maybe. 204 PSIG.
102.
410A.
72. Oh, 410?
410A. Yep.
72 degrees.
72 degrees Fahrenheit. So what do you think the temperature of that refrigerant is? If it's liquid and vapor.
72 refrigerant, so 72 degrees.
72 degrees. Let's see what the temperature of the room is. And, well, it's 70, so we're pretty close. This gauge is probably off a little bit. It's hard to see it. The problem with the analog gauges is that thickness of the needle. Trying to see how exactly what you're pointing at. So, yeah, 72 degrees. Temperature of the refrigerant is going to be 72 degrees. Is there liquid and vapor present there?
Yes.
Yes. So is it at saturation?
Yes.
Yes. So if we know the pressure, will we know the temperature?
Yes.
Yes.
Yes. Yes, we will. What happens if I drop the temperature of this tank? And what else drops? Saturation also drops. Yes. So let's, we did this the other night. I don't think we did it in a day class. We're going to put it in the freezer and let that happen. In the freezer. We'll return to that shortly. Alright, so saturation with liquid and vapor both exist. And so here we have some more of our notes. Superheat. What is superheat?
Temperature above saturated, which is above the boiling point.
Superheat. Sensible heat added to vapor above saturation. So what is saturation? Yep. Where liquid and vapor both exist. So now at when superheat, we're all going to be vapor. And can we measure it?
Yes.
Yes, sensible heat. Can we measure saturation?
No.
No.
No, that tank, I don't know how much liquid, how much vapor there is. I just know there is liquid and vapor. Superheat, though, we can measure it. Yes?
Well, can we measure saturation by PSIG converted to temperature? You just can't measure what percentage of what is in there.
Yeah.
By measuring the temperature.
We can find that it's at saturation, but I can't measure how much of it that's vapor, how much that's liquid.
But you're still, never, okay.
With a scale, I could use a scale and I can weigh it.
Yeah, no, I'm asking a different question. It's all right. It's the same thing that I was thinking.
We can find out where saturation's at by taking PSIG converted to temperature.
Right.
But we just can't find out how much of that is liquid, how much of that's going to be vapor.
Correct. I know, but yeah. I was just wondering, because you say it's not measurable, but you can measure the process that it's going on in the saturation point, and you can measure the temperature that it's at, which is the pressure, and you know the process that is going on, so it is measurable.
So we can measure where it's taking place at, but I can't measure. Remember, I can't measure how much of that is liquid. I can't measure how much of that is vapor. But here I know that it's vapor. I can put as I add heat to that liquid, is the liquid going to change temperature? No, it's not. As I add heat to it, more of it's going to boil, but it's going to stay at the same temperature. It's going to keep boiling, but I can't measure how much heat I'm putting into it.
Okay.
I can't measure the heat I'm putting into it. But once it all turns to vapor, I can measure how much heat I put into it, because the temperature will change.
So even if it's 90% vapor and 10% liquid, it's going to be the same thing as the same temperature as if it's 90% liquid and 10% vapor. So we can't tell that mixture based on the temperature. So
Right.
we're not measuring.
Same thing with ice. If I have ice water and there's 1% water in there, the rest of that's solid ice, what's the temperature going to be? Now what if it was 99% liquid and 1% solid? What's the temperature going to be?
32 degrees.
With the thermometer, it's going to say 32. We can't measure. We know it's at saturation, saturation, but we can't measure without looking at it. We can't measure how much that's liquid and how much is vapor. I can put heat into it. I'm putting heat into it, but I can't measure it. Now, once it all turns to liquid, and I'm putting heat into it, can I measure the temperature change?
Yes.
Yes, so that would be sensible. To where saturation is going to be all latent. As I'm putting heat into that, heat from the air is going into that refrigerant, making that refrigerant boil, but the temperature is staying the same.
So when you talk about measuring it, you're only talking about the amount of heat you're putting into it.
Right.
All right.
So basically, if it's saturated, it's the same temperature.
The only thing, yes, that's right. So when it's boiling in the evaporator, it's PSIG converted to temperature. Taking that PSIG, converting it to temperature is telling us where saturation's at. It's giving us a starting point. But we can't say, let's say that you're going to be saturated, you're saturated, and you're saturated. Okay, so how much liquid does this saturated have in it? How much vapor does this saturated have in it?
100% liquid, 0% vapor.
How much liquid and vapor does he have saturated at? How much? We don't know. You can't see. You know you're at saturation. But you can't see it. You can find out where saturation's at. Okay, saturation's right there, but I can't tell how much is liquid, how much is vapor. I can't identify. So anytime that we have saturation, let's say if it was water, what's the saturation point of water at 0 psig at sea level? Saturation point of water. 212. So that's the point that it's at, but I can't measure how much is liquid and vapor. If I just look at a thermometer and have a pot of water boiling, it's going to say what? 212. That could be 212 at 100% liquid. As it boils, it could be 212, 25% liquid, 75% liquid, 25% vapor. As it boils, it could be 50% liquid, 50% vapor. As it boils, it could be 75% liquid, 25% or 75% vapor, 25% liquid, or it could be turned completely into vapor. But what would the temperature be? 212. It's not changing. Were you putting? Did I have to put heat into this to make this change state?
Yes.
Yes. Can I measure that? No, I can't. Now, now that's 100% vapor, can I still put heat into it?
Yes.
Yes. What's the temperature going to do? It's going to go up. So here we got 213, 214, 215, 216. Can I measure the difference between where it changes state and what we're actually at?
Yes.
Yes. So I can measure that. I know that we are for sure 100% vapor. What do we want to make sure we have coming back to our compressor?
Vapor.
100% vapor. Why? That's a vapor pump. It will kill the compressor. And what does my metering device meter?
Flow refrigerant.
Yep, liquid refrigerant. So can I have vapor mixture come into that metering device?
No.
Nope. It needs to have all liquid. So how do I know that it's liquid? It's going to have to be below its saturation. So that means if I was at 211, 1 degree subcooled. 210, 2 degrees subcooled. All the way down. So anything down here is going to be subcooled. And a subcooled is below saturation. And superheat will be above saturation.
Oh, there's this saturation also called condensing point.
Yep.
But
So,
saturate-
okay, so let me just, that little segment right there is very important. If I'm going this way, what am I doing?
Evaporating.
Evaporating or boiling? Now, if I take heat away from it, I'll start going in which direction? This direction, so it's condensing. Still at saturation, right? So if I'm going this way, I'm condensing it from a vapor to a liquid. And if I go this way, I am boiling it from a liquid to a vapor. The opposite of boiling is evaporation. The opposite of evaporation is condensing. The opposite of condensing is evaporation, boiling. It's just which direction, that just specifies specifically which direction you're going. Here I'm absorbing heat into the refrigerant. Here I'm rejecting heat into the refrigerant. Okay, now the next part of that.
Wouldn't its condensing point be like 32 degrees or something?
You're thinking of ice.
I don't know. Yeah, I don't know.
You're thinking of the freezing point. Freezing point's a complete different thing.
Yeah,
Boiling.
Yeah.
Boiling. Changing state from a liquid to a vapor.
Is at 212. So then anything under, what, 212 technically would
Yep.
be the condensing point.
Nope.
No?
212 is the condensing point.
Saturation.
Okay.
They're both saturation.
So anything under 212. Oh, so 212 is where it would change back from a vapor to a liquid?
212 can be both condensing and boiling.
Yep.
It just depends if it's turning into a liquid or a vapor.
Wouldn't it be technically called subcooled liquid?
Below 212 will be a subcooled liquid.
Yeah.
Anything below that point will be a subcooled liquid. So you got water. It's room temperature 70 degrees in the room. So 212. The actual. Can you measure the temperature of that water?
Yes.
If I put a clamp thermometer like we have in the lab and clamped it on that bottle, what would it show? 70 degrees. Let's just say 72 for simplicity. 72 degrees. That's the actual temperature. What is the saturated temperature though? Can you actually put a thermometer on saturated?
No.
No, but we get the pressure and I convert that to a saturated temperature. So for water, the saturated temperature is a conversion of 212. 212 minus 72, what's the difference?
140.
So that water in your cup is subcooled 104 degrees.
40.
140. I'm dyslexic as well. So 140 degrees below its saturation point. Its saturation point at this pressure is 212. The temperature of it, if we put a thermometer on it, I can't actually put a thermometer on saturated, but I can put a thermometer on that water, and if I put that water in a copper pipe, I can put a thermometer on it and get the temperature of it. Well, the temperature of that water is 72. That's 140 degrees below its saturation. So what, if I can't see in that bottle, what's the state of that water in that bottle? What's the state it's in? It's in liquid. Now we can look at it and see it's in liquid, but in the units we can't look at it. But we know that its saturation point is 212. It's at 72. It's 140 degrees below that saturation point. It's for sure a liquid. Subcooled liquid. Yeah. Yeah, no?
Yes.
Yes.
And if we had at 0 psi at this pressure, and I had water vapor at 300 degrees Fahrenheit,
88 vapor.
it would be a superheated vapor. So 300 minus the saturation point of 212 is, it's what? 88 degrees. Superheated, 88 degrees. Steam.
Right now we're using water as an example to talk about the status, but what about inside the system? Since the compressor adjusting the pressure inside, so
It is, but I can do the same thing with water. If I raise the pressure of water, what happens to my saturation temperature? It goes up. So if I put this in a pressure cooker and change this this to being, say, 300 degrees Fahrenheit, my saturation changed with what? Pressure. So now, what would I be here?
Saturation.
I'd be at saturation. How much of this is vapor?
We don't know.
We can't measure it. We don't know. So, but now, if you had that, if it was at pressure, let's say, I don't know, just go throw a number out here, say 100 psig. So 300, and that water, the actual temperature was at 72. So 300 minus 72?
228.
228 degrees subcooled liquid. By changing the pressure, I change the boiling point. If I put water in a vacuum, let's say 10 inches Hg, put it in a vacuum, water will very easily boil at 100 degrees Fahrenheit. It will boil. Water will boil. You saw it the other day. Water boiled at 100 degrees. So if I had water, it changes state. Its saturation point's at 100 degrees, but it's at 72. What's 100 minus 72? 28. So now it'd only be 28 degrees subcooled. And if it was at 300 degrees, it'd be 200 degrees superheated.
Yeah.
Our saturation point is going to change every time we have a change in pressure. Yes. The key is I can manipulate boiling, I can manipulate condensing by manipulating the pressure. Which brings us to this very, very, very important point here. When the temperature goes up, what else goes up? Pressure. And when we know that when pressure goes up, what else goes up?
Saturation.
Yes. By raising the pressure, I raise the saturation point to make refrigerant condense at a higher temperature. But when I also take the temperature drops, the pressure drops, if I drop the pressure,
You drop the saturation point.
I also drop the saturation point. And that's how we manipulate boiling, that's how we manipulate condensing, and by manipulating saturation. And by doing that, I can have refrigeration, moving heat from a place that's unwanted to a place that makes little or no difference, or a place that we could use it more efficiently. Right? Make sense? Answer your question? Everybody else good so far? So far so good? All right, so our refrigeration cycle. What do we start with?
Compressor,
A compressor.
vapor pump.
Yes, vapor pump. What does it do?
Pumps vapor.
Pumps vapor.
Moves the refrigerant. It sucks a LP, low pressure vapor, and it pumps an HP, high pressure vapor. It is without a doubt a vapor pump. What line comes out of the compressor?
Discharge lines.
It is a discharge line.
Hot gas line.
It is a hot gas line.
High temperature.
And the state of refrigerant is a, yes, high temperature,
High pressure.
high pressure,
Superheat.
superheated vapor. And what component do we go into?
Conventions.
The condenser, the condensing coil. This just simply represents those pipes that are going back and forth. What's the first thing that happens in that condensing coil?
Saturation.
Superheat. It's superheated. We have to de-superheat it. Can you measure superheat?
Yes.
So what kind of heat is this going to be? Sensible. After I de-superheat it, I'm trying to de-superheat it down to what point?
Saturation.
Trying to de-superheat it to the saturation point, which is most of that coil.
So it doesn't have to be at the saturation point by the time it gets into the coil, just.
That's right. We have to get it. We have to get it down to that saturation point in the
okay.
coil.
So that's
And
why
it-
when it's going through it, temperature's dropping, and then when it hits the saturation point is when it would convert back into a liquid. That's why it's not measured. All right.
Am I supposed to take one, Pass?
I'm gonna pass around. I had a whole bunch, but I only have one. But if you want to put this in color, there's I got some crayons. So there's reds and blues. If you want to represent it in color,
Should I just take one and then pass it?
red and blue. You don't have to. I just it really helps for a lot of people. It's in color. I draw it in color every day. Red's representing what?
High pressure.
High pressure.
So I got when it doesn't have to be at saturation temperature when it enters the condensing coil.
That's correct.
Okay.
And the very first section of that condensing coil, that little at the very top, that little bit, doesn't take very much. The job is to de-superheat it. It's going to be all vapor, superheated vapor. So we have to cool. We have to take the heat out of that. We have to literally cool that. If it was steam, we have to cool that steam off first. Once I cool the steam off, I now get back into saturation. And it may be a big temperature change. It may be a 100-degree change. Numerically, it's a big number. But how much actual heat movement is there? Very little. Very little heat transfer. So the very first thing that condensing coil does, number one, it has to de-superheat it. And we can measure that. Not that we do very often, but we can. The next part that's happening is extremely important. This next part, what state is it in? Once we de-superheat it, what state do we end up in?
Saturation.
Yes, saturation. So right here, what's a refrigerant at right here?
Saturation temperature.
100% vapor. All right, and so this, and saturation, what's happening in saturation on the red side? Condensing, yes. Condensing. And then condensing means changing state.
From vapor to liquid.
Rejecting
Yes.
heat.
From a vapor to a liquid. And that is rejecting heat also. But what kind of heat is it rejecting?
Latent.
Latent heat. Is this de-superheating rejecting heat too?
Yes.
Yes, but it's sensible. Here's where the magics happen. We're changing it from a vapor to a liquid. We're rejecting latent heat. And latent means hidden. And also latent, you could also, if you wanted to add this, a lot. Right? Latent also means a lot of heat. So far so good? Condensing. Now, here, here it's 100% vapor. What about halfway?
50-50.
Mix.
Yeah, 50-50. What about here at the very bottom, right here?
Mix.
99-1.
We'll just call it right here. Let's say we finally get to 100% liquid. The temperature of this, is it above, below, or equal to the air temperature?
Below. Right above that.
Above, because this needs to be warmer than the air to get heat to leave. Now this, is it equal to, above, or below the air temperature?
Above.
Above, because we need to have a temperature difference to have heat transfer. So saturation has to be above the air temperature to get the heat to leave the refrigerant and go to the air. Now here, it's 100% liquid. Is it going to be equal to, above, or lower than the air temperature? Still above. We're still getting heat to leave the refrigerant. It is above the air temperature. But the difference is, right here, it's 100% liquid. It's above the air temperature. So what will happen? Second law of thermodynamics. There's a temperature difference. We're going to have heat transfer. The heat from the warmer refrigerant is going to go to the cooler air. But now that we're 100% liquid and I'm taking heat out of it, what's that called?
Condensing.
We already condensed it.
Sensible heat.
Sensible heat. What do we call that?
Subcooled liquid.
Yes! Subcooled liquid. Yes. Subcooled liquid. Can we measure that?
Yes.
Yes. So it's what kind of heat? Sensible. Ah, you see it now? Now, here, it's superheated. So is that above, equal to, or below saturation? Above saturation. Here I'm changing from vapor to liquid. Is that equal to, above, or below saturation? It's at saturation. Here I'm subcooled. Am I equal to, below, or above saturation? Below. Look at the beauty of that. Above, here's saturation. Above that, I'm superheated. Below saturation, I am subcooled. You can see it right there, huh? So we have to take it all the way down to saturation. Now it starts to rain liquid refrigerant. Now that's all liquid. Now I can drop the temperature of that liquid below saturation. So all of this has to be warmer than the air temperature. As subcooling, are we still rejecting heat?
Yes.
Yes. Still rejecting heat. Arrows. So now we're in this line right here. What's the name of this line?
Liquid line.
Liquid line. Yes. What's the state of refrigerant in this line? It's a warm, high pressure, because it's red, subcooled liquid. How much of it's liquid? 100% liquid. All right, what's an accessory that we go into? Yes. Liquid line, filter dryer. Liquid line, and it does this, it filters, and it also dries. What is it drying? What is the dryer part doing? Moisture, H2O. There's a difference between liquid and water. Water is in liquid form, but water is water. We could have liquid nitrogen. Is that the same thing as liquid water?
No.
No, but they're both liquid, but they're different chemicals. What's the arrow on this filter dryer should point to which direction?
Away from the condensing.
Away from the condensing unit and towards the metering device. Yep. And what component do we have next?
Metering device.
The metering device. Yes, the metering device. And if it's a fixed metering device, it means it's just simply a what? Restrictor or a, which is correct, but it's what?
Expansion device.
It is an expansion device. It's a fixed orifice. It's a fixed what? What's an orifice?
A hole.
A hole. A metering device is nothing more than a
Fixed
hole. A hole. A hole, and that piping, is that not going to have back pressure on this side, high pressure on this side?
Yes.
They're not going to have a pressure drop on this side?
Yes.
Absolutely. It is a hole. Some of the holes are fixed. A fixed hole means the size of the hole does not change. Other holes are adjustable, which means the size of that hole will open and close. That's all that means. So this has two names, the metering device also called an expansion device. And what it does is it restricts what?
Flow refrigerant.
Restricts or meters from a high pressure liquid
Pressure mix.
to
Low pressure,
a low pressure.
mixed substance.
I want to add a word. What word
Saturated.
Yes, that's exactly right. A low pressure saturated mixture. What do you think that mixture is coming out of this metering device?
75% of liquid.
Approximately 75% liquid.
25% flash gas.
Ah, 25% flash gas. Heard of Flash Gordon? This is the flash gas. 25%, bam, immediately flashed into a vapor. Did it change state from a liquid to a vapor?
Yes.
Yes, immediately. So anytime a substance changes state from a liquid to vapor, what does it do?
Boils.
Absorbs heat. Yes, it absorbs heat. What is it absorbing heat from?
The refrigerant.
The remaining 75% liquid that's there. So what happens to the temperature of the rest of this refrigerant? It drops. Instantly drops. There's another word for that. It's also called adiabatic expansion, but we're going to leave that out. All right, so coming out of the metering device, what state are we in?
Saturation.
Saturation. Immediately in saturation. Most of your evaporator coil is saturation. So saturation means, in this case, evaporating,
Going from a
boiling, which means it's changing state from a liquid to a vapor, and that's absorbing heat, and that's latent heat. Change of state. So, if I have a pot of water in the stove and I put so much heat into it to where all the liquid left, can I still heat up the vapor?
Yes.
Yes, that would be called steam, but in this case, we're going to call it what?
Superheat.
Superheat. So the temperature of this refrigerant is still below, it's still going to be below the air temperature. So can it absorb heat?
Yes.
Yes.
Yes. So now it's going to be superheat. Superheated vapor, and we can measure that, so it is sensible heat. So this line, what's this line called?
High pressure.
Suction line.
Suction gas line. And the state of refrigerant?
Low temperature,
Low pressure.
superheated vapor.
Low temperature, but the refrigerant is a superheated vapor. Is it gaining heat in this line?
Yes.
Yes.
How do we help prevent it from gaining heat?
Insulate.
Insulate it. Yes, and we come back to the compressor. So here, coming into the compressor, what's the state of refrigerant?
Gas.
Low temperature, low pressure, superheated vapor. Coming out of the compressor, what's the state of the gas, the refrigerant? High temperature, high pressure, superheated vapor. So here, can superheat be low temperature?
Yes.
Can superheat be high temperature?
Yes.
Can superheat be low pressure? Can superheat be high pressure? Yes.
Because on the other side,
So according to the refrigerant, superheat just means that it's above its saturation point. So it's going to be a vapor. Here it's vapor coming in. Here it's vapor coming out. That is a refrigeration cycle. So far so good? You sure? Okay, so let's add a little bit to it. We'll get back to where we were before we left. Can I measure how superheated it is here?
Yes.
Yes, I can. How do I find out how superheated it is there?
take the temperature of the low pressure line and
The actual
temperature.
suction line blank degrees Fahrenheit
Minus the saturated PSI
minus
temperature.
the suction saturated temperature equals
If there is.
superheated vapor. So if we look at this, can you actually put a thermometer? Can you actually find the suction line?
Yes.
Yes.
Can you actually put a thermometer on the suction line?
Yes.
Bam. Can you identify which one's the suction line?
Yes.
So if you can identify the suction line, you can put a thermometer on the suction line. Can you find the actual suction line temperature?
Yes.
Good. Now the next word says suction saturated. Which color is this written in?
Blue.
Which gauge is the suction gauge?
Blue.
Ah. So I need my suction. So it's going to be the blue gauge. And it says the next word.
PSIG.
There we go. So that's here. Oh, everybody, I want to hear from everybody. Saturated.
PSIG.
Saturation, PSIG converted temperature. So this very outside numbers right here is PSIG. So if I take these PSIG, I convert that to a
Temperature.
saturated temperature. So now it's a temperature minus a temperature. Can you have temperature minus pressure?
No.
No. Can it have cats minus bricks? No, it doesn't make sense, right? I need all cats or all bricks. So here we're going to convert our pressure, which is worthless, into a saturated temperature that I can use. That line temperature should always be above my saturated temperature, and I'll have a number to put right here. If any case you get a negative number here, there's something wrong. Because that maybe means that your clamp isn't clamping very accurate, or maybe it's a cheap clamp, or maybe the thermometer's off, or maybe you're using the wrong pressure conversion, or maybe the gauges are off. Something's wrong. The lowest you can get down to is you can get down to saturation, but it should be pretty well impossible, because what would negative superheat be?
Saturation.
Negative superheat would be a liquid. And since I'm at low pressure and I'm absorbing heat into it, it's really pretty well mathematically impossible to get a liquid. So if you put it in this order like this and you get a negative number, that's an important thing. A negative number means, something's wrong. I should never have a negative number. Something's wrong. I need to find out what's wrong. Make sense? So it's an important thing. That's why we always want to have this number on top. Is my suction line temperature warmer than saturation? Yes. So my suction line temperature should always be, that's what's happening, that should always be warmer than saturation. So it's a good thing to have it in this order, so that way if you get a negative number, you know, hey, there's a problem. There's something wrong. I need to find out what's going on. There's some kind of an issue. Cool, huh?
Unintended.
This formula, it's really, really important to know. If you have that formula, if you can memorize that formula and put blanks in it, you can just write the numbers in. How many formulas have I had you guys learn? What two?
That one and then the other one?
And the one we're fixing to do next. That's it. Now, when you get into the book stuff, you guys probably seen all kinds of formulas are thrown in there. Not having you learn all this. You can use even the one at temperature conversions. You can Google it. Convert Celsius to Fahrenheit, Fahrenheit to Celsius. Google it. Put the number. As long as you can find the number, you don't need to go through all that math anymore. I used to teach it before we had all the fancy apps and stuff that did all that. We used to actually have to do the math to convert it because some stuff comes in Celsius. You got to convert it to Fahrenheit. I don't see the purpose in that anymore now that we have the technology. You have the tablets. There's even apps that do conversions for you, but you can just Google it. If my phone were recorded, I would say, okay, Google, and converts 72 degrees Fahrenheit to Celsius, and it would do that for me. So there was a little worksheet in your homework. If you hadn't got to it yet, you should. That converts it from all different temperatures, all different temperatures.
There was a lot of them.
A lot of them, whole lot of them. And really what it means is, how low can we go?
Which scale? 0.
Absolute zero is how low we can go. Absolute zero on my Rankine scale is called 0. Absolute zero on my Fahrenheit scale is minus 460. On my Celsius scale is minus 273. And on my Kelvin scale is also 0. And then we also have the point at water freezes. Water freezes at 32 degrees Fahrenheit. Water freezes at 0 degrees Celsius. And water freezes at 273 degrees Kelvin. And water freezes at, what's 460 plus 32?
492.
What's that?
492.
492. That's the same point. It's not a different point. It's just different numbers representing that point. And if we have water boiling, water boils at sea level, 212 degrees Fahrenheit. So 212 plus 460. 600 and what?
74.
672 degrees Rankine. Water boils at 100 degrees Celsius. So 100 plus 273, so it'll be 373 degrees Kelvin. It's boiling here. I'm not changing water boiling. All these different numbers represent the same thing. Here's water freezing, turning from a liquid to a solid. All those numbers represent the same point, and this is the lowest point you can possibly go. All these numbers represent that same exact point.
Rankine is the exact same thing to Fahrenheit as Kelvin is to Celsius?
Yes, exactly right.
All right.
Yep.
Well, that's easy. Okay.
We don't use Rankine and Kelvin very often.
Right.
Actually, the only time I've had to use it, I think, was with a blood cooling thing. But just couldn't use that. Convert it over. That's all you have to do. There's formulas. If you look at that, there's a formula going from Fahrenheit to Celsius, and a different formula going from Celsius to Fahrenheit. No.
The app is pretty good.
The app, use it. And there's going to be an app for this we're going to use later today, but it's very, very important to know how this works and what's happening with this. This one's the one that really, really got to know. Got to know it. Right, and the other formula represents what? Subcooling. So we're going to start out, it's going to be opposite. So here we're going to have liquid. Liquid what?
Saturated.
Saturated. Yes! Right on, I like it. Liquid saturated.
PSIG converted to temperature.
Liquid saturated.
PSIG.
Liquid saturated.
Oh, PSIG to temperature.
Saying it makes it a whole lot more memorable. If you have other people saying it and you're just okay, then we get out to the lab. It's like, how do I find saturated? I'm going to yell at you. Liquid, PSIG converted temperature. What color is it written in?
Red.
What does red represent? The high pressure. What color is this gauge? Whoa! It's what a coincidence.
It was planned out that way.
Liquid saturated, and it's a liquid saturated temperature minus the actual liquid line temperature equals
subcooled temperature.
Subcooled liquid. It's a warm subcooled liquid. According to your feelings, it's going to be warm, but according to the refrigerant, it's below its saturation point. If you had water at 200 degrees, is that a subcooled water or superheated water or saturated water?
Subcooled.
Subcooled. It's 2 degrees below its saturation point. But if you were going to pour that on you, you would consider that very warm, right? But according to that water, that liquid, it is a subcooled liquid. So that's why we don't use the hot and cold stuff. We got to think, according to the refrigerant, it's a subcooled liquid. Okay, so far so good? Mm-hmm. So, if you wrote, even if you don't memorize, if you just write this down word for word for word, and we get out to the lab and you're like, oh, I don't remember. If you have the formula written down, you don't have to remember it. Liquid, saturated, PSIG converted temperature. Red, PSIG is the very outside numbers. PSIG converted to temperature. How do we do that? With the app. The app will convert it. Or we could also use the old-fashioned temperature and pressure chart. And we used to get these charts out. But the chart, let's look at 410A on this chart. Let's see, 410A. So let's look at the pressure changes. We go from 43 to 49 to 55 to 62 to 70 to 78 to 87 to 97 to 107 to 118 to 130. Then we start jumping to 140, 155, 170. See the big gaps between them?
It's not very specific.
No, it's not. So you're having to look at your needle and those analog gauges trying to see exactly what it's pointing at. Some go in increments of 5, some go in increments of 10. So you're trying to see where that needle's pointing at, and you're already off a little bit there. And then you're having to guess on this chart, well, between which number is it pointing at? So you can be pretty far off just with that. And then we go over here, and then it jumps in 40, 45, 50, 55, 60, jumping in increments of 5. So if you're between those two numbers, the two numbers there, you're going to have to guess. And between the two numbers here, you're going to get a guess. And you end up over between two numbers there, and you kind of got to guess. A lot of guessing going on. Well, guess what? I don't like guessing. They make pressure charts like that have a lot more numbers on them. But there's they'll take up a lot more space. And there's 200 and something refrigerants. That means there's 200 and something of those charts you got to keep around. So that means you're going to carry around in your pocket a stack of papers that big folded up with all these different refrigerants in your pocket, right?
No, you're fine.
Oh, no. Oh, that's right. We have these really awesome apps now that will do it. There's tons of them. I just picked one. We're all going to use the same one just so I can answer questions on it. And you're going to convert saturated pressure, PSIG, into a saturated temperature. And that's the temperature we're going to use, and it's a lot more fast. It's a lot more accurate. Questions? So what we're going to do first is we're going to go to the lab, just like what we did Thursday, and we're going to get superheat. We're going to get subcooled. We're going to put the gauges on the proper way. We're going to get superheat. We're going to get subcooling. And then we're going to take gauges off the proper way without losing any refrigerants and without getting hurt. And we're going to put the liquid back in the system while the unit's running. And then after we do that, we can cycle them off. We're going to come back in here and we're going to add some more stuff. Okay? All right, let's go. Let's do it to it.